reminding that I was muted. So welcome to Earth Sciences 2203, Environmental Geosciences. As you'll see with the picture I'm starting with here, what I'm hoping we can do during this semester is learn an awful lot about the Earth, its systems, how it plays a role in environmental sciences, public health, and sustainability. Obviously, it'll be a bit of a different semester, but as you saw in the email, I'll be doing lectures through synchronous lectures. I'll be recorded for your viewing later. And today, what we're going to do is kind of go through the background of the course, make sure everybody knows what they're getting into. I think, in general, most people taking this course find it to be quite interesting, rewarding, and not too much, not overwhelmingly stressful. So hopefully, you all share that feeling by the end of the semester. I apologize to make sure my microphone's not muted in the future. Okay, so what is environmental sciences? Environmental geosciences, rather. One of the few things I want to talk about is what this course will introduce you to. And basically what we're going to focus on is a broad range of topics that foster an understanding of the physical structure of the Earth and the evolution of the Earth, how it's evolved to affect the environment and human health and human evolution. We're going to talk about the processes that have formed our planet, how they do things like place energy deposits, critical resources, water, and how in some cases, like having a fault line near you, can lead to geological hazards. And it will be a common theme of the course, at least as the way I teach it, is that we're going to discuss some of the key concerns and questions surrounding resource development utilization. This will span everything from water access and availability, managing things like droughts for water, drinking water use or irrigation, all the way to energy use, energy environmental impacts, and even climate change in and of themselves. So in and of itself, rather. So we'll definitely discuss these concepts and challenges of resource development, geological hazards, water issues, environmental pollution, environmental health, and basically hopefully will lead to an understanding of how we can mitigate things like climate change and develop a more sustainable society in terms of the key resources we want to adapt. One of the key things I like to remind everyone is if you can't grow it, you have to basically harvest it from the earth, whether it be it water or resources. So a lot of what we're going to talk about is sort of discussing the geological and human factors that influence how we sort of successfully manage and develop resources. As a sort of requirement here, I'll go through the expected learning outcomes. I hate to insult you by reading these things, but we're instructed to do that this year especially. So our goals here are to make sure students understand the basic facts, theories, and methods of modern science. That students learn key events in the history of the science, specifically as it pertains to environmental geosciences. That students are provided examples of the interdependence of scientific and technological developments. And that'll be a major theme of our course here, is a systems approach or an Earth systems approach, that we can figure out how the various things fit together and how changing one parameter in geologically or environmentally can influence the system and affect many things within it. And also hoping to foster an environment where students consider and discuss the social and philosophical implications of scientific discoveries and understand the potential of science and technology to address problems of the contemporary world. So that'll be some of the main GC learning goals we're going to try to foster throughout the course. And particularly, what I want you to come out of this course thinking about is having an awareness of how all these systems are interrelated and how all these things sort of fit together. I won't sit here and bore you with reading an academic misconduct statement. It's in the syllabus. It's the same as probably every other class you've taken. I don't typically have any problems with this. If you could do me the favor of not cheating, we'll all get through this together, but it's there in case anyone needs to go back to it. And anybody who needs additional support or services, by all means, it's very different online especially, but these resources are available to you. Let me know, or let the Student Life Disability Services Office know if there's anything additional needed to help you in support of the class. I'm happy to help any way I can. And going through the sort of logistics of that, an additional resource is, of course, my office hours. We're gonna do double office hours this year. It's gonna be Monday, Wednesday from 10:05 to 11:10, which is basically after class. Each Monday and Wednesday. So by all means, you can email me at any time. I'm usually relatively responsive within 24 hours to emails. If not, Carmen works well. I check in pretty regularly, but I'll have a standing open Zoom hallway after class at 10 to 11. In general, though, I'll state that it's better if you shoot me an email before or during class saying, hey, I'd like to talk to you afterwards, so I can make sure I reserve time for everybody. But I can meet people through Zoom after class. So I'll go through the logistics. These are the questions people always concern themselves with, and I'm going to go through each one of these in general. I tend to be a faculty member who doesn't worry very much about the grades, and I definitely design the course and the grading scheme so that you're designed for success. As you can see here, the exams 1, 2, and 3, midterms, if you want to think about these, I think almost as extended quizzes. They'll all be online. They're worth about 15% of your grade each, and the final exam is worth about the same amount. So it's actually, I would call it a semi-cumulative. There will be some material that will advance throughout the course, but most of the final exam will actually be based on the material we cover towards the end, and that's largely because the course is going to build upon itself as we go through the semester. One of the things that I actually thought would make this reduce everyone's stress, but maybe early on has caused some problems, is there's a weekly worksheet. They're basically an online quiz. They're set up that you can try to do the quiz. If you get the wrong answer, you can get another chance at it. You're more than welcome to have you use Google or use whatever resources to help you answer the questions in the worksheets. What you'll find pretty early on, though, is that the worksheets are just designed to make sure you're keeping up with the class notes. So almost basically every single question they'll ask you in any of the worksheets, and they won't all be as simple as this week's, which has 5 questions on it, but every question that's on the worksheet will be out of the course lecture notes. And that'll make up 40% of your grade, so you'll be able to sort of keep you focused on the material we're going through, prepare you well for the exams, and also make sure that everyone has a good basis of points going into going throughout the semester. One of the key things about the weekly worksheets that you'll see is that, which are basically set up as multiple choice, short answer, or true/false questions, is that they will not just be preparation for exams, they will literally give you an idea of the types of questions I'll have in exams. And I think the rubric I've been using in the past is about 40 to 50% of the questions that will show up in exams are actually from the weekly worksheets going throughout the semester, so you'll should have no trouble getting prepared for your exams on time. Exam dates are on the syllabus. I don't anticipate any changes regarding exam dates, but if we need to do anything different, we can of course we can talk about that later. But for now, I think the syllabus, the exam dates posted on the syllabus online are probably remain the same. In terms of grading, there's one additional aspect of this, is that by pop quizzes, they won't be during the exam, they won't be during class. I'll send out an additional worksheet on occasion if I see folks aren't participating in the worksheets, and pop quizzes can only be used as bonus points. So point I'm trying to make here is that if you have a rough go of it on one exam, or you miss some time from worksheets and you're having trouble getting caught up, there'll be sort of bonus online pop quizzes that'll be available to help you bring the grade back up and ideally keep you at or above 100%. Here's the grading scheme, standard grading curve. A grading scheme. There is no actual curve, but as I said earlier, I designed the course that if you come every week, at least participate either in the synchronous lectures, or if you participate in following up on the lectures online afterwards, you should be able to certainly get an AA minus in here, and that's what I like to see everybody get. And if everybody can do that, I'll be happy to give everybody A's. The only other aspect of the syllabus I was going to mention is that we do have a course textbook for the class. It's on the syllabus, the environmental geology course textbook. I think it's very useful. It's very helpful. I think it's a high quality book. I get the question every first lecture of every semester, so I'll just cut it off here since I won't be there in person to talk with you. Is that if you don't want to buy the book, if you want to buy the used book, or if you don't feel you want to have that, that's fine. That's your discretion. I will tell you that's the book for the course. But what you'll find in my lectures in my class is that basically most of the material on exams is going to be from the lecture notes. I'll highlight the things I think are important, and I've distilled the things that I think are important from the textbook into the course notes. So if you don't want to buy the book, that's at your discretion, and no pressure to do so. But it can be a very valuable resource, particularly if you want to move on in this type of work. So with that, of course, if anyone has any questions about the syllabus, questions about the grading scheme or the general setup of the course, feel free to email me. I'll get back to you later today about that, or we can set up a meeting, relatively shortly. But that's pretty much the nuts and bolts of the course, and hopefully it's relatively self-explanatory. One thing I wanted to mention about the worksheets, I know there's a little confusion. So what will happen with the worksheets is that each week they are due by midnight on Friday. Hopefully no one's working anywhere near midnight on a Friday on these. These should take you 10 to 15 minutes to complete a week, I hope. The way it's set up is that they will automatically post. The whole semester is already set up, so they'll actually automatically post at Sunday at 5 p.m. There's no pressure to do it then either. But the exception was this week. It was set up to do, set up at 5 p.m. the day before the semester started, which I'll probably change in the future based on the number of questions I got with that. But you'll have the pop quiz, or the worksheets will post on Sunday at 5 o'clock. You'll have almost a full week to work through them. Shouldn't take you long. If there is a pop quiz that week, it'll also post at Sunday at 5 p.m. So everything at Sunday at 5 will be there for you to work on throughout the week. And the way it's done is typically that the answers to the weekly worksheets are going to be based upon material cover in that week's lectures. So it'll kind of keep you up to date and thinking about things contemporaneous with the components I'm going to be lecturing about. So rather than stopping and asking if there's questions, given the Zoom format, again, if you have any questions, email me. I'll try to be responsive to it as quickly as I can. And if anybody has a question in terms of being on Zoom, I do tend to notice the chats in general, but if I'm slow on it, let me know. If anyone wants to stop and ask me a question through chat, that's greatly appreciated. I must admit that I much prefer the interaction with students and enjoy the opportunity to sort of hear what everyone's asking. In regards to the lectures, I just saw the question on chat. Is that yes? We all the lectures when they're done will be posted to Carmen. So the recorded lectures again will be on Carmen. Now the reality is the conversion of those files takes about 45 minutes based on a 55-minute lecture. If I go that long, I won't always go that long given the online format. But the point being is that it might take me till around noon on the day that we have the lectures for everything to get online, but it all will be there. I assure you, the very latest by the end of that day. So I know it's a new world we're all living in terms of thinking about classes and things like that. So I am gonna transition into moving into covering some of the big format materials of the course, get you an idea of where we're going to go and how I want you to think about this course. But I promise you, we won't probably go for the full time period today, and we won't hit you with anything that's too hard to think about in the first day back. So, where I do want you to think about, where I do want to start the frame the course for this semester, is think about our home, which is Earth, and think about Earth as a very dynamic source of energy, source of mineral wealth, source of life, source of, in some cases, hazards, of course, of panic in regards to things like earthquakes and volcanoes. So the way I've designed the course, the way we're going to proceed through the course, is that I'm going to start out by sort of setting up the framework of the course today and probably on Friday. And then what we'll transition to is actually thinking about our home, thinking about how the Earth was formed, how the Earth has evolved, and what's the modern Earth look like in terms of both the geological hazards, the resources, and the best efforts to manage those resources on planet Earth. So from the beginning, what we'll do is go through how the Earth evolved. We'll talk about some of the more important geological processes that can influence in the environment, sustainability, and public health. These can relate to things like volcanic eruptions, which are both hazards and also are a renewal of resources that can have a major influence on economics and other aspects like that. We'll spend some time talking about earthquakes and all the associated hazards related to earthquakes. Here's a few examples of, with example tsunamis and collapsed buildings. These are, volcanoes and earthquakes. We tend to think of them as big episodic geological events, and they certainly are. But the reality is that even compared to something like, COVID, there are episodes in geological history where things like earthquakes and volcanoes in particular have actually killed even more people than that. So these can be very relevant to understanding a sustainable environment moving forward. We'll also talk about the risk factors that affect flooding and why we're particularly in light of climate change, how these risks are increasing and have greater aspects of damage to property and to human life. We'll talk a lot about land use and droughts, and basically go through all the geological and Earth systems factors. So basically, the things that Earth does and things that we do to the Earth that can influence all these factors. So there'll be an emphasis on things like climate change in that regard. But what we're really going to try to focus on throughout the semester is what created the Earth system we're interacting with, and how we can build innovative strategies for sort of managing these concerns. So before we move forward and jump into the sort of science of the Earth systems that we're dealing with, I think we really need to think about where we are in society. Okay, obviously it's 2020. It's been one heck of a year so far, but in reality, there are a lot of other factors that have been building up for a long time that influence the world we live in today. And I'm not going to tie this to Corona in any way, shape, or form. But one of the things I want everyone to think about here is a few of the things I want people to think about are population growth. Right, the human population, the Earth, the population on planet Earth has never been what it is now. I think we all sort of know that implicitly. But what we may not recognize is just how rapidly population growth has changed throughout our lifetimes, and certainly my lifetime, our parents' lifetimes, grandparents' lifetimes, to the point where you've actually seen exponential growth since within the last 300 years, and actually nearly a doubling of population growth in my lifetime. Born in 1981, and in that time frame, I'm not even 40 years old yet, and the population's nearly doubled. For those of you who haven't thought about this very much, there's about 7.8 billion people on planet Earth today, and there are due to be over 9 billion people by 2050. Each one of those individuals needs water. Each one of those individuals needs food. Each one of those individuals needs energy consumption. And from a world population perspective, the single biggest risk to the Earth systems, and this relates to climate, water, food, and energy, are the fact that the world population is increasing exponentially and actually getting extremely, extremely high. Not that that's a bad thing implicitly. It's just that we have to actually think about creating an environment where we can sustain an equal access to those resources for all those individuals, which is a problem we've faced forever. One of the highlights I'm going to give you, this ties the ideas of water, certainly climate change, land use, and even food together, is the fact that one of the statistics that I find overwhelmingly mind-boggling to consider is the fact that although the population's doubled during the last 40 years and has went from about 3 billion in 1960 more or less to almost 8 billion now, the per capita energy use, the per capita water use, and the per capita use of almost all resources, land use, food, particularly in the meats, has all increased commensurate with that population growth. So it's not just that there's more people than there used to be, it's that there's more people and each one of them is using more of each of the resources than they have in the past. So you can see where it becomes quite an appalling, or not appalling, but perhaps horrifying to try to consider how we can make sure everyone has equal access to resources such as water, energy, and food. And this just puts in perspective. This graph I'm showing you now will show you will show you the rates at which energy consumption has changed over the last within the last 2 centuries, and you can see that just like the population growth, you're seeing an exponential increase in the amount of energy consumption. One of the main things we want to highlight in thinking in terms of sustainability and thinking in terms of Earth systems and how to manage these things together is, of course, the fact that we're not all using energy, that all of the global citizens are using energy at the same rates. There's not the same per capita energy use. When I was in undergraduate, taking courses like environmental geosciences, one of the big debates was the fact that America was the largest user of energy, was the largest emitter of CO2, and was only 2% of the world population, something like that. And I'm not providing a value statement at all. I'm just stating that in the last 20 years or so, the world's changed quite a bit. We've seen a lot of rapid development in Southeast Asia, in the Middle East, and certainly in Africa. And simply put, providing the same standard of energy, water, and food access, which is our goal. Make sure there's equality in terms of access to resources for all the global citizens that we enjoy in the United States, providing those same levels of energy, water, et cetera, in Southeast Asia and the Middle East and China. Middle East, specifically in China, as you see here, is one of the biggest users now. And Africa requires us to really think hard about how we can improve access to certain resources and sort of equalize the access to resources in these aspects. So to give you some perspective about why this has changed, why are we seeing such a change in these things, is basically increasing changes in technology. Early on, the Industrial Revolution, of course, started with the steam engine. We've seen the generation of electric motor, mobility or transportation, lighting, commercial aviation, television. All these things were parts of the increased energy demands. And really, since about 1960 on, you'll see this flip-flop in technologies between innovation that provides new energy resources to try to mitigate these aspects, and then changing components that add more demand, like computational skills, the microchip computers, the internet. An interesting statistic, at least interesting to me, is that today 11% of all the energy used in the world on any given day is used just to run the internet, okay, and store electronic data on computer storage devices. So clearly that's a lot of energy use in an ever increasing population that we weren't even dealing with in any major way 30 years ago. So all these things sort of lead to the idea that we have to find ways to innovate, create sustainable models to reduce energy demand, reduce water demands, and we're going to spend a lot of time talking about that throughout this semester. One of the main topics, and we won't be focused entirely on energy throughout the semester, but one of the main topics related to that is where we're actually accessing energy from. This will give you a graph here, shows both the total energy usage through time, but also shows you where the energy came from. And one of the things you've undoubtedly talked about, certainly in your generation, is this increasing gap of certain renewable energy resources. So increasing solar, wind, and geothermal in the last, is predicted to be a major aspect of the next generation. What's sort of interesting about that is that from 1980 to 2019, the total percentage of American energy production by renewables has actually remained about the same, 9 to 10%. What's actually changed throughout the last 20 years, throughout your generation, is largely a shift from hydroelectric, dams to things like solar, wind, and renewable. And there's great promise, as I show you here, that we're expecting these to increase in the percentage throughout time. But in saying that, and these are some of the factors we need to consider and spend a lot of time on throughout the semester, is that you'll notice that even out by 2050 here, so we're only here 2020, even out by 2050, the best case projections still place about 60 to 65% of all the energy demands being met by fossil resources, crude oil, shale gas, natural gas from other deposits, and coal, and only about 30 to 40% being handled by things like biofuel and renewables such as hydroelectric, solar, wind, geothermal, and nuclear. And one last comment on that is that since this graph is made, there's actually been a very big change in the projections where most of that nuclear power is actually now expected to not probably come online since we've sort of stopped building them. So this is just an example, thinking about energy, of one aspect where we have to recognize there's a great demand for increased energy access, but not necessarily an easy solution, right? In essence, there's plenty of oil and coal to go around. We can continue on the path we have been developing on. We can certainly start to develop those resources more in the areas, the regions of the world where there's increased energy demand, so Southeast Asia and Africa, for example. But those have implications that are global in terms of carbon dioxide and climate change and all those aspects like that. So, so for perspective, just like the energy demands, not all the energy production consumption are in balance, regionally. So there's still a lot of energy used in just transporting materials and resources like coal and oil around the world. In essence, there's two arguments here. One argument is that, well, if we're going to provide equal access to resources, then we're going to have to rely on developing fossil fuels. And there's the other one, which is that we can't really keep going along this path of increasing population and actually manage climate and environmental concerns related to that. So we have to recognize that we have to innovate and develop new ways, such as solar or wind, to provide energy. Another aspect regarding this that we're going to spend a lot of time on, I'm focusing on energy here as an example, but we'll do this for geological hazards as well as other anthropogenic or human-induced aspects, is just the environmental impacts of all the decisions we make. So, I'm just showing an example here from something that was, I don't think this news story example was, but was many in Ohio, was that, there's a lot of controversy a few years back about not just the climate impacts of using fossil fuels like fracking natural gas, but also the realization that there could be other water contamination issues, things like stray gas, anything that leaks out of the wells and gets into people's water, as well as other contaminants that are spilled on the surface, were a concern that might influence environments. And this is a picture of an individual, actually from Pennsylvania, who could light her water on fire because of a well that leaked into her water well. Not always the case. In fact, I've worked on that problem a lot. It's a relatively small number of times that happens, but in certain situations there are a variety of environmental impacts that can influence. There are a lot of environmental impacts that can result from different types of energy use. This one's from shale gas, but of course, many of you may be aware of other examples. Does anyone? I want to ask you to actually respond. Does anyone, when you think about this, think about this particular image is over here in the bottom left. This is actually acid mine drainage relating to coal mining. And on the right here is actually a picture of the Kingston ash slide. Basically, it's coal ash and coal particulates. There was a dam impoundment by a plant there that actually failed, and millions of pounds of ash and dust were released into the river and caused a variety of environmental problems. So, the point I'm trying to make here is that in all of the choices we're going to make, we talked about this in terms of energy today, we have to recognize there are going to be sort of environmental costs that have to be associated with these factors, and we'll spend some time going through those and discussing those throughout the semester. So, one of the of course, like essential issues of our generation is thinking about how all these decisions influence climate on a global scale. Just like I talked about the fact that we would like to optimize resource access equally across all the global citizens, we have to recognize that those decisions, if we, as different countries make them or we make them collectively, that utilize things like fossil fuels and increase the carbon dioxide levels in the atmosphere, influence climate, and that has impacts all the global citizens. Unfortunately, as we'll talk about throughout the semester, it tends to be that the most at-risk populations are often the ones that are most influenced by those climatic changes. So one of the aspects we'll talk about a lot in terms of climate and other energy and environmental problems is sort of this Earth systems process where every time we change one factor, it influences all the other factors, and it leads to a variety of sort of nexuses around water, food, energy, and environment that we'll discuss throughout the semester. So this is actually a little bit out of date, I suppose, but of course this is something you all know. I think this is an answer to one of your quiz or worksheet questions for this week. But one of the things I want you to be aware of are, as we think about every decision we're going to discuss during class, and even just think about responding to geological systems like volcanic eruptions. Volcanic eruptions themselves can be major emitters of carbon dioxide, and all these geological and human-induced processes all are in a balance in the Earth system that we need to consider how they'll influence things like CO2 levels. So the answer to your question is that the CO2 concentration is increasing. So if you're doing your quiz while you're taking care of class here today, recognize that CO2 is continuing to increase. And this curve, by the way, I probably won't put it on an exam, but it's very famously called the Keeling curve, after the person who from Scripps Institute of Oceanography that actually first identified that CO2 concentrations are increasing. These are all from the Mauna Loa Observatory out in Hawaii. And I won't touch on this kind of detail in class. Don't worry about that, but just provide some context there. The curve is called the Keeling curve, Keeling. And the observations are always taken the same island, Mauna Loa Observatory out in Hawaii. But I have this other question here with these oscillations, and people point to this a lot. If there are people who are sort of climate change detractors, point to these oscillations and changes throughout geological history. So you don't need to worry about so much for today's lecture, but know that by the end of the semester you'll be able to understand what those oscillations mean and why. And just to give you a sense, this oscillation on this sort of annual basis is actually related to seasonal changes, and that's the decreases are when the northern hemisphere goes into spring and summer, and we see agricultural and forestal blooms, and then the increases are the fall, winter, when leaf litter and other components decrease. But we'll talk about that more later in the semester. So where we're going to get to today is what concepts we're going to link together, and clearly. The biggest threat to the environment, and I'm not saying we should stop this, I'm just saying we have to realize it's true. The biggest threat to the environment are understanding that human population growth. Human population growth, as I've already alluded to, is already probably beyond the carrying capacity of the Earth in a sense, in that we need to develop new innovations for energy, water, and food in order to sustain the population we have as it is. Clearly in the last several generations, we've made great strides in that, but we've also seen really dramatic increases in population growth during that time. We're going to talk a lot about linking this through sustainability. Again, sustainability, the key aspect here is providing continued equal access to all resources, and that can be from actually getting water, getting energy, or actually just access to clean air to the whole population of citizens on planet Earth. And then the last component will be coming back to the idea of thinking about the Earth as a linked Earth system, recognizing that both geological and human processes can dramatically affect systems. I think there's not a better example or more clear example of that than thinking about how increasing CO2 levels from burning fossil fuels, sort of a necessary evil to meet energy demands, if you will, can influence many aspects of the Earth systems, including increased temperatures, melting of ice caps, loss of habitat, changing ocean acidification. There are a whole compendium of things that can be related to these processes. So I guess to this point, that's sort of a summary of some of the main themes. These themes of human population growth, sustainability, and linked Earth systems will be implicitly or explicitly a part of pretty much every lecture throughout the semester. I hope this isn't scaring away, but if you don't want to hear about those things, you probably won't love the course very much. We'll often come back to those examples about how that will be, how those things tie together, particularly the linked Earth systems, at least after we build a model for how of an understanding of how the Earth formed, evolved, and whatnot. But each of those will be key themes that we're going to spend a lot of time learning about in and throughout the semester. Okay, so what we'll do now is we'll get started on just thinking about this human population growth. I'm going to give you some basic background related to this, and then we'll wrap up there for today's lecture in just a few minutes. So the first thing I want to highlight your attention. This is not implying the Earth is only 10,000 years old. This is just looking at a scale of the amount of growth in human population throughout the last nominally 12,000 years. And if you notice, it doesn't matter when humans started. Maybe it's 2.1 or 2.2 or 3 years ago, whatever the debate is currently in anthropology, where Homo sapiens evolved. On a scale comparing it to the current population of planet Earth, which is, this is out of date at 2000. By 2020, it's 7.8, so almost up here at 8 billion people. We can't even observe the number of people on the scale that were actually present for most of humanity. So the first question I want to introduce you to, the first concept I want to introduce you to, is the fact that what happened 12 to 13,000 years ago that actually started allowing human, Homo sapiens, human population to increase dramatically. It's not just the ability to start fire or the ability to grow crops or anything like that. In fact, it actually is something that's innately geologic. And about 12,800 years ago, there was an event in geological history. I won't question you on the exact name of the event, but it's called the Younger Dryas event, which was a second period of glaciation of an ice age that followed a massive, about 100,000 year long ice age. And it was only as we came out of the ice age where areas like Europe and most of North America, certainly most of all of Ohio, was covered by ice as recently as about 12,000 years ago. And it's really only as we come out of that ice age in the last 12 to 13,000 years or so where we've seen human population start to increase. If we start to increase. So the second component is, how do we get to this 8 billion people? Okay, so the answer is really complicated and has a lot of aspects to it. But what I want to draw your attention to most importantly is the rate of increase is actually something called an exponential growth curve. And I think in reality, most of you have actually seen this growth curve, see curves like this, and realize there's exponential growth curves. What this implies, though, is that the population is not increasing linearly; it's actually increasing at an exponential rate, which implies that the rate at which something increases or decreases can be very rapid compared to the original concentration. That's what we observe in human population growth. Give you a sense of this. This sort of changes the scale and make it a little clearer to see. Is that most of the population increase slowly, linearly for quite some time, probably throughout most of human evolution, into about the 10,000 BC timeframe. And it's really the development of various types of technologies. The Stone Age, where we started to use stones; the Bronze Age, where we could start doing metallurgy; the Iron Age, where we refine metallurgy to make stronger tools, where we could start to see the exponential curve start to increase. What's interesting is that, with the exception of the bubonic plague, Black Death, in about it started about 1348, we've been on an exponential growth curve for about the last 12,000 years or so. But really, you get the sense of how long it took to develop the Stone Age, the Bronze Age, the Iron Age, and things like that. You can imagine, going back to the graph I showed you earlier, once you get to the advent of things like steam engines, electrical motors, the internet, the rates, computational things like computers, the rates of innovation are increasing dramatically, and population has largely followed that, with the exception of times where biological systems on planet Earth sort of greatly influenced the population related to the bubonic plague. There are minor variations along this trend that you can't exactly see very well. Some of them related to major volcanic eruptions. In localized communities, it can be can see things, populations dropping related to things like tsunamis on coastal populations. Obviously, a much larger scale during various other plagues and things like that throughout Earth's history. But key aspect I want to highlight here is, again, we're seeing a largely an exponential increase in the population of the human population on planet Earth, and that is largely expected to continue for quite some time. Again, projections are by 2050 to probably be about 9.8 billion people, and based upon current growth rates, which we'll talk about in a second, might get to just about 10 billion people by 2060, or make them up a little bit short based on decreasing growth rates now. So I introduced this idea of a growth rate. One of the aspects here, don't worry, I won't make you do any math in this class, but the growth rate is just the population at time 2 minus the population at time 1 divided by the population at time 1 times time 2 minus time 1 gives you a rate at which the population is growing. And the key aspects of the growth rate of population is that the population growth that is above 0 actually implies there's more people on average coming into the population, being born, than there are or immigrating into the nation than there are being lost to death or ex-migration or out-migration. So if you take a look at the global population, you can see that many of the sort of economic, more advanced economies of the world, the richer countries, if you will, actually have relatively modest growth rates. So U.S. is in the I think it's 0.7 if I remember correctly. Some of Western Europe falls in this category, but notice that a lot of Western Europe actually falls in even a lower growth rate. So places like France, England, there's still more people being born than are dying, or more people migrating in than are migrating out. But you'll notice that the rates are small relative, or just narrowly or marginally positive. And in fact, there's really only a few regions of the world here in Russia and Eastern Europe where you're actually seeing population growth rates below zero. This means that there's actually a decreasing or declining population, less births and in migration than deaths and out migration. But in comparison, I hope your eyes have already been drawn to this. Note particularly in poorer countries in Africa and the Middle East in general. I'm not trying to label them poor, but we're tying this more towards economic GDP outputs than anything else. You'll notice that the growth rates can be extremely high. So here, for example, in Democratic Republic of Congo, for example, in Central Africa, Sub-Saharan Africa, you can see the population growths are, up to 2.5 to 3 times above a positive rate. The key aspect here is that anytime the value is above zero, it's in growth. Negative values are in decline. And what you'll hopefully get the impression of is that, based on the fact that only very small parts of the world are actually in decline, that goes without saying that the population of the world's increasing. But obviously, that's geographically distributed, where you're seeing most of the population growth in Africa, Middle East, and Southeast Asia. In what formerly were called developing countries, now it's more deemed to be more appropriate to label them by economic capacity rather than judgmental value like development or developing. What this is tied to is largely the fertility rate. So the fertility rate is basically a metric for the number of children per woman in a country. And you'll see here in the U.S. I think it's 2.1 child per every woman throughout their lifetime. And most of the developed nations in Europe, Canada, Australia actually even fall below that. They're finding a birth replacement rate of in about 1 baby per population. I think the last I looked this up, Italy had the lowest growth rate or fertility rate in the world, just below 1 child per woman. But tied to that population growth we talked about earlier, you can see that most of that population growth is increasing dramatically in areas like Africa, where there can be 5 to 6, even 6 to 7 children per woman in some of those areas. Now, what's not really talked about in the fertility rate that you have to be aware of course, is the fact that the lifespan, or the sort of number of children that actually make it to adulthood, and the average life expectancy of individuals in some of those countries can be lower. So it's often hard to predict, but in general, over the last approximately 60 years, we've seen pretty much sustained exponential growth very rapidly of population. And where this goes, and I was bringing this back to the economic growth, this is a little bit out of date. It's only a 2009 statistic, but you'll actually see here's the total fertility rate. The number of children born per woman is negative exponentially correlated with the per capita gross domestic product. So basically, it's an economic metric of how much economic development there is in a country. So in general, the U.S. has about 2.1 children per woman, and you'll see that most of the fertility rate is tied directly to economic capacity of the country. So notable countries, Angola and Saudi Arabia, are both countries that have significant components of their gross domestic product tied to oil exports, and as a result, they are sort of fall off the line to the right of the curve, to the right, having more GDP perhaps than expected otherwise, and as a result, they still have relatively high fertility rates for their GDP. And Israel, which has a relatively high GDP per capita, but has a higher than normal fertility rate. But in general, this curve is a really good indicator of how fertility is tied to economics. That basically, as we have a greater economic capacity, we tend to have less children per woman in the population. So, some perspective on this. As the population increases, so will demand for energy, water, food, other raw materials, and as a result, as I alluded to earlier, the environmental impacts will also be tied to that. So, the projections right now for the United States are that by 2050, our population will hit about 388 million people. It's currently 331 million people. Last time there was the census is actually going on right now. We'll have a more reliable number soon, but last time there was a reported values by U.S. Labor Statistics. And give you a perspective on this, since where we'll end for the day, is that tells you that there's about a birth every 7 seconds in the United States, a death about every 13 seconds, a one net international in-migration every 40 seconds. And if you tie those all together, it tells you that the United States population gains a person every 124 seconds on average. So looking at that same time frame by 2050 on the world's population, we're anticipating about 9.8 million people. Depending on which model you use, we might climb over 10 billion people by 2050. We might fall just short of it. Most people are projecting that the best guesstimate is that about 9.8 million people is reasonable based upon the various birth rates, fertility rates across the world. And for perspective, as of this morning, there's 7.8 billion people nominally in the world. So it's fairly astonishing. I think to think about the fact that we already are facing major climate crises. We're already facing major water access shortages and major water inequity in terms of poorest populations not getting access to water and certainly high quality water. But what I'd like to end for today to leave you thinking about is that we have to recognize that within the next 30 years, we have to actually, find resources for another 2 billion people, but B, we have to recognize that we have to do a better job at actually providing sustainable access to resources in an equitable fashion for large components of that population. I talked about energy in the examples before. Just thinking about water, today in the world, there are about 2 billion people that don't have access to water for drinking water, sanitation, and hygiene. And I don't mean even at the level of the U.S. I mean just have reliable access to the actual water supply. And there's about 3 billion people who don't have access to water quality that meets the World Health Organization standards for drinking water quality. So if you think about that in perspective, that tells you right now at 7.8 billion people, nominally 40% of them don't have access to basic needs in water, particularly clean water, on a daily basis. And our goal is to make sure everybody has equal access, but make sure they have equal access with recognizing we're going to add 2 more billion people in the next 30 years alone. So you can see where the idea of population growth becomes a fairly staggering number to think about, particularly if we're going to actually stick to our ideal goals of creating sustainable access and equitable access for every individual. So where I'll leave you with finally is that in the amount of time it took me to say that, let's pretend it was every second is about 2 births in the global birth rate. So I don't even want to think about how long it took me to talk today, but quite a lot of people were born during that time. And that number is going to keep increasing. Even things like COVID, they sound big and certainly has been incredibly disruptive, but will be a minor blip likely on the global population growth curve. So we're going to end there for today. I'm going to spend the last few minutes of every class looking at the chat room, make sure I'm not missing anything. The worksheets are covered. Yes, the worksheets are covered in lectures throughout the week. You can complete them before the lecture. You can complete them anytime you want to. If you already know the answers, you can go for it. If you wait for the lectures, you'll certainly be given the answers during the lectures. Yes, the lectures again will be posted on Carmen after they are recorded. So later today, you'll see the lecture 1 pop up somewhere, and I don't remember the date for exams off the top of my head, but I'll make sure it's on. I think it's on the syllabus. If it's not, I'll make sure it gets there soon. Anyone who has any questions, feel free to email me, and we'll start regular office hours on Monday. I'll make myself available after class on Friday, but I have a few other meetings after class today in terms of organizing the class. So lectures will be up. I will always do a synchronous lecture during the class time, and you have the option of participating in that or in terms of watching the recorded lecture online, it'll be up. Shouldn't be up any later than middle of the day of the lectures. So. And I see some folks saying they can't find the data that the exam list syllabus. I'll make sure it gets there. I thought it was there, but I might have copied and pasted something wrong. I'll make sure it's there today. So I'm going to sign off. Thank you all for those of you who participated online for listening in. I very much miss being on campus and miss having a chance to talk with students and interact with them directly. So I hope we can wrap this up, and this will be our only semester doing this, but I'll do whatever I can to make the online experience as good as possible. So let me know if there's any issues, and I'll look into the syllabus stuff now. Have a good rest of your day, and see many of you on Friday, if not whenever you get a chance to watch the lecture. Have a good day. Bye.